We are eCubic MA Embedded AI enables ECG monitor to become analyzer. The objective of this project is to develop an embedded AI module that can be integrated with ECG sensor to create an AI-enabled device for screening arrhythmia and sleep apnea. We plan to employ HiMax WE1 Plus and STM32 for performing ectopic beat and sleep apnea classification based on overnight single-lead ECG signal using our own developed deep learning algorithm. We have trained and pruned the ectopic beat and sleep apnea deep learning classification model with high performance and compatible for embedded system development. An accurate and robust embedded AI technology will be developed to process complete overnight ECG recordings for performing arrhythmia and sleep apnea screening in the future. The global market size of ECG monitor devices is up to 1.4 billion USD, which will rise 19.58% because the growing need comes from the target audience, the elderly and cardiovascular disease patients. Most of the ECG monitor, up to 59.13%, is not only used for monitoring but for further diagnosis, which shows the potential of ECG analyzer. Our project then presents a fast solution to transform an ECG monitor into an advanced ECG analyzer. As our field application, we focus on the sleep apnea and arrhythmia. Ectopic heartbeats are abnormal heartbeats that originate from outside the normal electrical pathways of the heart. It is important to detect ectopic heartbeats because they can be a sign of an underlying heart condition, such as arrhythmia, which can increase the risk of stroke and heart failure. Meanwhile, sleep apnea is a potentially serious sleep disorder in which a person's breathing repeatedly stops and starts during sleep. It is important to detect sleep apnea because it can have significant impacts on an individual's health and quality of life. In the ectopic beat part, training database is the MIT BIH open source database. It has a variety of arrhythmia labels and we divided them into 5 groups according to AAMI standard. Contains with 47 subjects and over 109,000 samples. And for test database is AHA arrhythmia database from ECRI collected by American Hospital Association. Only 4 classes according to AAMI standard is included in the database. Overall, 154 subjects and up to 354,000 samples. In the OSA classification system development, we utilize an online database called Apnea ECG Visionet to be our training database. There are 35 participants in total. We excluded 2 participants' data from borderline and healthy control group, so we only employed 33 participants' data for training. We also plan to use Southern Taiwan Medical Center data for testing the trained OSA classification model, and there are 50 participants in total. In the ectopic beat part, the ECG signal was first pre-processed and sliced by 0.72 second windows, which is approximately 1 heartbeat. The single beat ECG signal would be transformed using CWT as the input of deep learning classifier. Finally, self-designed CNN structure S-embedded net was established using cross-validation. The S-embedded net structure is evolved from the classic AlexNet, but significantly smaller and has higher performance. In the development of OSA classification, the 7 to 8 hours overnight ECG signals were partitioned into subsequent 60-second ECG windows and were pre-processed. The EMD algorithm was used to obtain decomposition features, and the NCA was then applied to reduce the number of IMF as EMD features. Finally, a 1D deep CNN model was established using cross-validation. The developed 1D deep CNN model has much less parameters than the pre-trained CNN models. The project will be developed to process complete overnight ECG recordings for the purpose of performing arrhythmia and OSA screening. The device is expected to demonstrate high accuracy and sensitivity levels of approximately 85 to 90% and can easily combine with ECG monitor as an ECG analyzer. There are many limitations on the hardware, mainly on memory, storage, component size, and power consumption. The memory and storage of HiMax and STM32 are far lower than the embedded system on the market, and the processing speed is relatively low, but this also allows the power to be reduced very low. The self-designed CNN structure S-embedded net is a perfect balance between performance and model size. We evolved the AlexNet structure by reducing the number of convolutional layers, fully connected layers, and decreasing the size of the feature map. Utilizing different kernel size and the reduction of one convolution and one fully connected layer helped LMU EBCNet achieve 0.15 million parameter size, which is suitable for hardware porting compared to AlexNet and GoogleNet. S-embedded net, moreover, only contains 3 convolution layers and one fully connected layer, yet achieved the best overall accuracy with only 0.399 parameter size. The proposed 1D deep CNN architecture comprises input, feature extraction, classification, and output stages. We performed several pruning trials on the 1D deep CNN based on the number of feature extraction and classification layers in order to obtain the optimum prune model. The 1D deep CNN with 12 feature extraction layers and 2 classification layers was then selected as the best prune model. The best prune 1D deep CNN could achieve high performance with 1 MB model size, which can be suitable for the proposed embedded system, HiMax WE1 Plus. In the current hardware and software implementation, we have performed and ported the ectopic beat classification algorithm into STM32, including the ECG signal preprocessing, finding peaks, feature extraction, and deep learning classification, with the proof of excellent classification performance, efficient, and low memory usage. As the future hardware and software implementation, other embedded chips, HiMax WE1 Plus and NVIDIA Jetson TX2 will be used for conducting the ectopic beat and sleep apnea classification simultaneously. The overnight ECG signal will be further processed on the embedded system for feature extraction using CWT and EMD, then perform the ectopic beat and sleep apnea classification based on the trained deep learning models. And this is our preliminary result demo for ectopic beat classification. We use UR to transport the ECG signal in STM32. The pre-processing, including filtering and normalization, and CWT transformation are then computed in STM32. The S-embedded net performed and made the classification inferences based on the CWT spectrogram result and output the result through the GPIO and ignited the LED light of the corresponding classes. Our device has the following 3 E features. First, easy to use. It reduces the inconvenience of patients and speed up the measurement without causing any harm. Second, edge computing in ARM. Based on the powerful computing capability of ARC-EM90, we implemented an edge computing deep learning algorithm for detecting arrhythmia and sleep apnea. Third, energy efficient. The system can be driven by only using a mobile power supply and consume only 3.97 watts during operation. Comparing the ECG-related chips available on the market, most of them can only use measure ECG real-time and digital filter, but none of them have relevant disease identification. Our device can achieve AAMI arrhythmia classification, the delay is only 1.33 seconds, and have more transmission interfaces. The eCubic MA is targeted toward hospitals, clinics, and medical practices such as cardiologists and ENTs, as well as individual consumers who are interested in monitoring their heart health. Additionally, partnerships, exploration, and collaboration with ECG monitor suppliers can be conducted to expand its reach and provide comprehensive customer support to its target market. We are eCubic MA, care for your health, Taiwan can contribute.